Okay, thanks very much. Am I on? Yes? Good. Okay, so I'm going to talk about exchangeable arrays of random variables. This is not a talk about new research. This is really intended as a tutorial. So as many of you know, in probability theory, maybe 30 years ago, there was a development of a theory of these exchangeable arrays that have certain kinds of symmetry. And it already contains many of the objects and some of the same ideas as the more recent Lovász-Szegedy theory of limit objects for dense sequences of finite graphs. So that's widely appreciated, but I think it would still benefit this community to perhaps see a little bit of how probabilists think about these things. So I wanted to go over the statements of some of the simpler theorems from that area and then try and show you actually a proof of one of the main ones, the Aldous Hoover representation, and also sketch how it relates to the limit objects. Okay, so this is really a tutorial. Also, there are notes for this talk on my website, so you don't have to take notes unless you're opposed to the internet. So that's up there. There are some mistakes, which I know about, but email me anyway if you find anything. Okay, so let me first introduce the objects of study. Let's fix some nice target space E, and think of this as a closed subset of the reals, if you're worried about it, and an integer k at least 1. Then an exchangeable random array, well, let me be careful, a k-dimensional exchangeable array with values in E, is a family of random variables indexed by the set of all k subsets of the natural numbers. So all unordered k tuples of distinct natural numbers, where each takes values in E. So each of these random variables is E valued. And their joint distribution has this exchangeability property that the law is unchanged if you change the order of the natural numbers. And where, okay, if I have a permutation of the natural numbers, I let that act on sets by moving the individual elements in the obvious way. Okay, so that's an exchangeable array, k-dimensional with values in E. You could also make a similar definition where you index the family by ordered tuples or ordered distinct tuples, this sort of thing, and actually everything works out pretty much the same with just routine changes along the way. I'm going to focus on this for definiteness, but that theory is all very much parallel. Okay, so these were really first studied in the 1930s in the case k equals 1 by Definetti. So Definetti studied these in about 1930 when E was a two-point set, and then Hewitt and Savage did the case of general target spaces E in about 1950. And then there was an emergence of interest in the case of higher dimensional arrays in the late 1970s. So I'm just going to write some names. I think the first one is Hoover, who had an approach to looking at these things coming from logic and model theory. And he was the first to prove a structure theorem for these guys. We'll come to that in a moment. And then David Aldous gave a more probabilistic proof of the same theorems and generalized them. He was building on earlier ideas of Kingman relating to models of random partitions, which I won't talk about. And then after that, there was a further generalization due to Kallenberg, who more or less gave a complete theory for all k and all target spaces and all the obvious ways of tweaking the theory. It's also worth mentioning there is actually now a definitive textbook on this written by Kallenberg, Probabilistic Symmetries and Invariance Principles, easily available. Okay, so they were motivated, well, Hoover was motivated by logic, and apart from that, people were motivated by applications in statistics and also in geometry of Banach spaces, something called the stable subsequence principle in geometry of Banach spaces, which I won't talk about. But they thought about these things very much as probabilists, and the thing they wanted to understand was whether you can characterize the distributions of arrays like this as abstract objects in their own right. Can you characterize the measures, which are the joint distributions of this family of arrays? And the nice answer is that you can. So main results are structure theorems for all such distributions. So I'll state a couple of those theorems in a little while. Let me first just give you some examples at the risk of repeating things that we've heard already. The first and most obvious example of such a distribution arises if the random variables are IID. That's obviously exchangeable. Okay. This is the IID case. And then their joint law is just some product measure. So some product measure where nu is a probability measure on E. That's trivial. And the second example is more interesting and shows that there's more to this theory than just independent random variables. And this is what you get from sampling a finite graph. So I shouldn't dwell on this too long because we have heard it already. But if you fix a finite graph, VE, then one way of producing this exchangeable array is to sample IID, a sequence of vertices uniformly from V. So sample vertices VI in V uniformly at random, independently. And then you let the random variable xij, for an edge ij, take the value 1 if the sample vertices vi, vj are an edge, and 0 if they're not. So this is some random procedure that gives you an array of zeros and ones, and you can check easily that because I chose these in a symmetric way, this ends up being exchangeable. But this is really different from an IID example. So there is more to this theory. Okay.
So this is k equals 2, right?
This is k equals 2, yes. Yeah, so I should be clear. I wrote this for arbitrary k. This is only when k equals 2. You can generalize to hypergraphs, actually, but I don't want to talk about that. Okay. Good. So those are some obvious examples. And with those in mind, people ask whether that's essentially all there is. Is it true that, in some abstract sense, all such exchangeable arrays arise from sampling some nice structure? This is a slightly vague question, but I'll make it precise in a moment. I wouldn't be giving this talk if the answer weren't yes. So they do. You should think of this as sampling just independently, and this is sampling from this graph, which is a more complicated structure. And so now I can write down for you the general class of objects, at least in the case k equals 2, which you end up sampling from. Okay. I kind of don't like this business. I'm just going to go back up there. So actually, let me state the case k equals 1 first, the classical Definetti theorem, and then state the case with k equals 2. And those are the two that I will focus on in this talk. So when k equals 1, the Definetti-Hewitt-Savage theorem is the following. So here you have an exchangeable sequence. And the conclusion is that there is some measurable function f from the interval times the interval to E such that this sequence has the same law as the following. It's what you get if. I'll write it and then tell you what it is. So it's what you get if you draw uniform random variables from the unit interval u and another one ui for every integer. So u and ui and n are independent, uniform from the interval. And then for each I, you apply f to this pair, and that gives you a sequence. And because you chose these in an exchangeable way, what you get out is exchangeable. So for example, if there's no dependence on this first one, then this is an independent sequence of random variables. So that's that example 1 that we had before. So example 1. Take, let me just say f to be f of ui, i.e. it doesn't depend on the first one. And more generally, if you do have a dependence on this first guy, what you get is a mixture of product measures, a mixture of IID sequences, as this choice of U varies, you fuse U first. Once that's fixed, then what you get is an IID sequence. So that's the classical Definetti-Hewitt-Savage theorem. And now again, when k is 2, things get more interesting. So this is the, I'm going to call this the Aldous-Hoover theorem, although the exact attribution is a little unclear. So, this is when k equals 2. So now suppose I have this array indexed by unordered pairs, exchangeable. Then the conclusion is that there is a function f measurable from the interval times the interval squared times the interval to e, such that the array I started with has the same law as the following. Now I'm going to draw independently uniform 0, 1 random variables, one by itself, one for every integer, and one for every pair, and apply f to tuples in the following way. For u, ui, uij, independent u, 0, 1. There's a little wrinkle here, which is that this is indexed by unordered pairs, so we'd better make sure it doesn't matter which way round I put these. So let's say this is symmetric in the middle two variables. So let's just say middle symmetric. Okay, so that's the statement of the Aldous-Hoover theorem. And what you should think of is that we're sampling from this measurable function f. So the law of this guy I'm going to now refer to as samp f. So the theorem says that any exchangeable array has law equal to samp f for some f. Okay? So let me quickly try and make this a bit more concrete by going back to the graph example. Okay? It's written here. So suppose x arises in the way that I'm removing. You have a fixed graph, you sample IID vertices from it, and then you join integers if the corresponding vertices are joined in the graph. So that was example 2. Given the graph VE, what you can do is the following. You partition, suppose that V has m elements. You partition the unit interval into m equal subintervals. And now the function f is as follows. Actually, f isn't going to depend on the first variable. I don't need that in this example. It's also not going to depend on the last one. I don't need that in this example either. Only depends on the middle two. And it takes the value 1 if these two guys happen to land in a pair of cells with a partition where there's an edge, and 0 otherwise. So if ui is in I, k, v, uj is in il, and KL is an edge of the graph, and 0 otherwise. So you might say that in this example, I'm only using the level 1 randomness. I'm only using a function that depends on this one-dimensional sequence. I could, in principle, produce more general examples by putting some dependence here or here, but you don't need it for this one. Okay, so is the statement clear, at least? So the theorem says that these exist. There's an obvious question then of how unique they are, and I'll come back to that in a second. And then I want to spend most of the time in this talk. Yeah. Oh, yeah, no, this is a partition into equal size pieces. Yes. So I think what I want to do is spend most of this talk actually showing you the probabilist or a probabilistic proof of this. Something that's been buried in the literature for some time, maybe is not so widely known in combinatorics. It does require a little bit of serious measure theory. You have to be comfortable conditioning onto a general sigma algebra, or at least you have to be comfortable letting me do that. And then, so hopefully by the end I'll have shown you pretty much all the steps in this proof. But before I go into that, I want to quickly describe the relationship between this and the graph limits. Okay? Are there questions at this stage anymore?
Yes, I understand the analogy between the U in the two-dimensional case and the U in the one-dimensional case. I'm not sure I understand the role of the UIJ, which your example didn't depend on.
Right, so if instead I produced a random array by choosing zeros and ones all independently, then I would only be using UIJ. So that was the case of example 1. Okay. So now let me tell you a little bit about the connection to graph limits. So suppose now we have a sequence of finite graphs, which we'll think of as being dense. So then for each of them, I can sample some 0, 1 array from them, as I just did, and that produces a law. So sampling gives UN, which is a probability measure on the space of all assignments of zeros and ones to the space of edges. PR. Okay. And exchangeability says that this is invariant under the action of S infinity. Okay, well this is a compact metric space, and so measures on it have a vague topology or weak star topology, whatever you want to call it, that's compact as well. So I can talk about Cauchy sequences and limits in the vague topology. And now the following is really an easy exercise. Mu n Cauchy in here for the weak star topology, the vague topology, is equivalent to this sequence being Cauchy in the sense of left homomorphism densities. Let me just say left Cauchy. And if you check, you'll find this is because the finite dimensional marginals of mu n really are just counting the left homomorphism densities. They're the same numbers. So this is a direct correspondence. So already this has put the mu n's you get from graphs into some compact space where the two notions of convergence match up. So if you want a compactification, there's one right there. You take the closure. But what's more interesting is that actually the kinds of limit that you get, as described by the Aldous Hoover theorem and as described by the limit object theory, match up as well. So to see this, let's suppose first that we know what the limit object is for our sequence of graphs. In the sense of left homomorphism density or the cut metric of any of the other equivalent notions. And the theory tells us that it should be some function w from 0, 1 squared to the unit interval. And now just again, comparing the formulae for left homomorphism densities, you can read off what f, or an example of what f ought to be. You find that then mu n converges to some f where, now this is a little bit scary, but it's not really, f, say x, u, x, y, w, remember x is a function of 4 variables, actually isn't going to depend on u, and it's going to depend on w in the following way. It's the indicator function of the set where w is less than or equal to big W of x, y. Okay, so that looks a little bit strange, but what you should think here is that this is just some choice of function f with the property that if I integrate in the last coordinate, I get back w. And that's actually all that I need. If you go back to the formulae for the probabilities of finite dimensional marginals, you find that this is exactly what you need to make this limit measure match up with the homomorphism densities given to you by W. So if you know the theory of left convergence, then you can get the Aldous Hoover theorem from that, provided you know that your exchangeable measure is a limit of things sampled from finite graphs. Okay.
Does this give us that there is only a single f up to or a single?
That's a separate analysis. It was done by Kallenberg in '89, but it's a separate piece of work.
So we could get the uniqueness theorem by appealing through this to.
Yes. Okay. Let me just talk about the other direction.
Does
I don't know about sets of measure 0. There are problems of things that are not quite bijective. Yeah. Probabilists have ways of magicking away sets of measures. But it's, yeah, basically it's the same problem. So just to make this quite clear, on the other hand, if we know that mu n converges vaguely to some mu, well, being invariant under S infinity is clearly preserved by taking this kind of limit. So this is still an exchangeable measure, so it's equal to sum f for some f. And now if you just write down what the left homomorphism densities are here and here, you find that you've learnt the following. Vn En converges in the sense of left densities to W, where, and now there's going to be a little wrinkle which I'll remove by waving my hands. Wxy is the integral of f x y little w dw. The same formula is up there. The wrinkle is that the theory tells us there should be a dependence on u as well. Actually, that's easily removed by just muttering ergodicity. The point is that these are all ergodic measures. In this case, the limit is still ergodic. That's not a universal fact in ergodic theory, but in this case, you can check the limit is still actually very strongly mixing. And if it's strongly mixing, it's easy to see f really can't have a serious dependence there. So you've recovered W. So if you want to introduce limit objects, here's a cheap way to do it. If you know the Aldous Hoover theorem, you simply put all your measures into the space of put all your graphs, into the space of exchangeable measures by sampling, take weak star limits there, apply this theorem, and write this formula in your home. Yeah, multiplicativity. That's, yeah, you can actually check. They're mixing in this very strong sense that disjoint events are, the probabilities multiply. And then the dependence on U is gone. That's right. Okay, so you can see the correspondence is really very strong. If you go to the case of larger K, the corresponding structure theorem was worked out there as well. This is work of Kallenberg around 1990. And then you get a function f on a cube of dimension 2 to the k. This is similar to what Gabor-Elek and Szegedy produced in a different approach using ultralimits. I'm not going to go into that here, but again, the correspondence is really direct. Okay, other questions at this stage? Yeah.
So, regularity seems to play an important role in the graph limits characterization. Does anything replace it?
Can I come back to that question after I talk about the proof?
Okay.
I think maybe I can say something more helpful then. Okay, so I'm going to spend most of my time trying to prove the Aldous Hoover theorem, but let me first say one more thing about uniqueness. I think I'll give you a proof of this theorem only when the target space E is a two-point set. That simplifies my life. And in that case, I want to use this W that we just wrote down to write a more explicit formula for the statement of the theorem. So suppose E is 0, 1. Then simply using this conversion between f and w that you can choose, given f, you integrate out the last coordinate, that produces w. The Aldous Hoover theorem is equivalent to the following. For any exchangeable mu, there is some w on the unit interval times the unit interval squared to the unit interval. This is that first coordinate which I've had to put back in the general case. I just argued that by ergodicity it's not there when you have a limit of graphs, but in general it does need to be there. So there is a w such that for any distinct edges I1, J1 up to IM, JM, the probability that the array takes the value 1 at all these locations equals the following. So on the right, what have I done? I've again drawn my family of, yes, that's right. I've drawn my family of IID uniform random variables. And inside here, I've formed a functional of them, which is the product over these distinct pairs of edges of these quantities. And then I take an expectation. And we've all seen this formula for left homomorphism densities in the limit where you have an integral over a cube. This is just a probabilist way of writing that. It's an expectation instead of an integral. It's the same thing. So that's actually what I want to prove. Okay? So it's worth remarking here that in the f language, the limit is less unique because any function f that has the right integrals on vertical fibers will do. They all give the same model. So there's a non-uniqueness there. In general, if you have a more complicated target space, it can be nicer to work with f than w, because then w has to take values in the space of probability measures on E. Gets a bit messier. Okay. But this is what I'm going to try to prove, this guy. Great. Okay. Okay, so I think I'm now going to launch into the proof, unless there are more questions. Okay. So this proof is sort of a little bit like magic. The first time I saw it, I looked back and I couldn't really see where anything non-trivial had been said. But there is something non-trivial, and I'll try and make some remarks about that at the end if there's time. So the first thing I want to do, this is the raw statement of what I'm going to prove, but the first thing I'm going to do is make a different assertion, which will actually be the heart of the theorem, and then argue that this follows from this different assertion. So the main claim is the following. Again, we're given our array, indexed by edges in n. And now I claim that there exists some auxiliary nice space Z. Z will actually end up being some compact metric space. It's a product of finite sets. You'll see explicitly what it is a little bit later. But some auxiliary space Z and a Z-valued exchangeable sequence, say yi, coupled to the original array. So what that means is that this is a family of random variables, and so is this, and they live on the same probability space. They have some overall joint distribution. And now here's the key thing, or two key things. This coupling must be such that everything together is still exchangeable. And there's some formula which I'll write down. So, coupled to those such that 1, the array yi xij, which is now indexed by ordered pairs of natural numbers, is exchangeable. And secondly, and I'm going to write some scary formula which you shouldn't take too seriously just for the moment. Secondly, can you all see down here actually? Yes? Okay. So this is a little bit scary, but you should think it looks something a little bit like that. And I'll talk more about exactly why it's like that in a moment. The first thing is just to clarify this. Given those yi's that I've constructed, this is now an array indexed by ordered pairs, because this pair remembers which is I and which is j, but I can still talk about exchangeability. It just means that if you permute them using some permutation of n, the law doesn't change. So the same definition as before. And I'm going to ask that that holds. And then I'm also going to ask for this second property. So this says that among the x's, if you want to compute one of these events, you have a finite list of distinct edges. If you want to consider the event that the array takes the values 1 at all those edges, and any event, any finite dimensional event can be written as a combination of these, then the probability of that, conditioned on knowing what all the y's are doing, so conditioned on the values taken by all the random variables yi, factorizes in this nice way to the probabilities of these individual values 1 appearing conditioned on knowing only these two. So this is an assertion of conditional independence plus a little bit more. It's saying that these random variables xij up to xi1j1 up to ximjm are conditionally independent given the yi's, and also that then the distribution of each of them conditioned on all the yi's really depends only on these two. Does that make sense? Yes? Yes, all y's. Yes. Is that clear, at least as a statement? Okay, so my assertion is that if you know this, then you can actually get that fairly easily, and then the heart of the proof is proving this. Okay, so I think let me first try and show you quickly why this implies what I wanted, and then most of my time will go into this thing.
The YIs are like the homomorphism densities, the densities of the...
It's not quite so simple as that. I'll show you. You'll see in a little bit. Let me first go from this to that guy. Okay. So let me move these things around somehow. So let me try and show you how to deduce Aldous Hoover from this. I'll rub off the first half because that's easy. And this deduction, this completion of the theorem, actually uses Definetti's theorem as an ingredient. So I'm assuming the case k equals 1 of the theorem to prove the case k equals 2. So to deduce AH, use Definetti, or Definetti-Hewitt-Savage. So what I'm going to do, it's a little bit silly, really. I'm just going to say, okay, let's define a function g from z times z to the interval 0, 1. In the following way, g of z1, z2 is simply this formula where I condition on that being z1 and that being z2. So this is now a symmetric function on z squared, symmetric by the exchangeability. So I can simply go back and rewrite that with g of yir, yjr in here. So I haven't done anything, I've just changed notation. But now by Definetti, is a problem? It's okay. By Definetti, because the yi's are an exchangeable sequence, I know how to represent those. So there is some function h from the interval times the interval to z, such that this sequence has the same law as this sequence, h, u, ui. So now all I'm going to do is say, well, if these are actually equal, then I get an equality in law if I feed this into here. So that implies that probability of x equals 1, given the yi's, is equal in law to the product. We can leave a space here. To the product r equals 1 to m of g of h of u, uir, h, u, ujr. Except I've done something a little naughty now, but I shouldn't really say this because now the yi's are here, but they're not there. So I made a little mistake, actually. What I should have done was integrating the y's first and then write this. So once you have this equality of conditional probabilities, you can integrate over the values of yi and get an equality of unconditional probabilities. So this is not quite legal, but if I say this and this, now it's legal. Does that make sense? I've really just substituted things in. Well, conditioning on the yi's and then integrating them out, that's the same as not conditioning them, conditioning on them in the first place. And over here, why don't I just define this thing to be w of u, uir, ujr. So I'm done. Okay, so that was actually pretty trivial once we know Definetti's theorem. Does that make sense? Yeah. I'm really sorry, I didn't hear the question. Yeah. I have two distributions, say, real valued random variables, and they have the same distribution. then any function of them still has the same distribution. No. No, this is really pretty confident about this one. Really, any functional of same distribution random variables is still same distribution random variables. That's safe. Yeah.
Maybe this is a conditioning on sigma fields that I pretend I'm comfortable with. So you condition on Z1 and Z2 are elements of infinite compact matrix, not compact space.
Yes. So
Conditioning on this,
right. So G is actually only well defined almost surely.
by this condition.
It's a regular conditional probability. Yeah. Yeah. Is that okay? Is that more or less okay? Okay. There's a huge, very ancient literature on why I'm allowed to do this. So I'm going to defer to that. But modulo these major theoretic difficulties, this is really just changing notation and substituting everything in, and then here's the formula we wanted. The hard part is proving this, the thing on the middle board. So that's what I'm going to spend most of my time on. Okay. And now I'm afraid that the slightly cowboy attitude to sigma algebras is going to get worse. Not too much worse, but a bit worse. So let's make a start on that. So the first thing, I want to make another small claim, which again sounds a little bit like magic, but it's actually very easy. So small claim. Once you have your array indexed by edges in n, you can actually find an array indexed by edges in Z, such that what you started with is the top quadrant. So given can find an array indexed by edges in Z, such that the subarray indexed by the positive edges is what you started with. So let me just say which is consistent. Okay, so this follows fairly quickly once you know the following.
You want to say it's exchangeable?
Yes, I do. Thank you. This is still exchangeable, now for permutations of Z. This follows because the following slightly mysterious fact: exchangeability implies, of the original array, that xij has the same law as x gamma I gamma j for any injection gamma from n to itself. So by definition, exchangeability tells you this when gamma is a bijection, but actually once you know that, you get it for all injections. And this is for, again, silly measure theory reasons. These laws are determined by their finite dimensional marginals. If you fix a finite set of edges, so a finite dimensional marginal and an injection, I can always just choose a bijection which agrees with that injection on that finite set and does something different somewhere else. So for that finite dimensional marginal, I can simply verify this by writing out the corresponding thing using that carefully chosen bijection. Because the marginal was arbitrary, these are equal. So in this mysterious infinite world, knowing something for all permutations gives it to you for injections right away. Okay? Once I know this, all I do is, so now I choose any bijection say pi from n to z, any bijection you like. Using that, if I start with this array, I can always just write it as a z-squared indexed array instead. And what I get doesn't depend on pi by exchangeability. And now using this fact, the quadrant inside the positive edges has to be what I started with, because you're just composing pi with an injection. It's still an injection of n. Does that make sense, or did I say that too fast? Okay, if you don't stop me, I'm going to keep going. Yeah?
It's not much different, but couldn't you also just do it in a more standard way by saying you start from negative n to infinity, then n tends to infinity?
Yeah, but I don't want to just say that. I mean, that's true, it is, but I don't want to just say that. He's right, though. It's the Kolmogorov extension theorem. You just, for any finite marginal, you can guess what it ought to be, and they're obviously consistent however you do it by exchangeability, so there's a big measure. Okay. Let me go up here now. I don't know what to do now. Okay. So this is the proof. So I can find this bigger array where the original guy sits inside it. And having shown you how quickly this follows, you think, well, that's trivial. That couldn't possibly be useful. But actually, it is useful, because now I have a huge list of other random variables that I didn't start with, and then they're what I'm going to use to define the yi's. So now define, and let me just write it down. For I, a positive integer, yi will be the following. It's the random variable that remembers all these 0, 1 values in the negative edges and all the 0, 1 values for an edge that connects I to the negative integers. So let me write this down and then I'll draw you a picture. So n complement for me is just the non-positive integers. And yi is just going to be the random variable that remembers all of these x values and all of these x values. These are indexed by the edges between negative integers, and these are indexed by the edges between I and some negative integer. So let me go over there and draw a picture. So you think of these arrays as being indexed by points in the plane, and they're symmetric, so let's actually just look at the part of the plane that's below this line. So these are all the edges in Z. The original array is what's indexed by these points. And now for yi, I simply let yi be the random variable that remembers all the 0, 1s down here and the 0s and 1s on this line. Okay, that's yi. For completeness, let me tell you what space it takes values in. It's obviously the space 0, 1 to the power of this index set times 0, 1 to the n complement. So that's a countably infinite product of finite sets. Give it the Tikhonov topology. It's compact and so on. Okay? So all that's left is for me to show you that with this assignment, this actually works. I get the formula I wanted. The formula I wanted is there. Let me move these around. Okay. There. So now the formula I want is this one. And I want to show that if I just make this choice of these random variables, I get it. Okay. So let me next make another little rewrite of the problem. Again, using very standard properties of conditional expectation. So that's property 2. 2 will follow if we show instead, and then I'm going to write another scary formula, but it's a little bit less scary. Yeah?
Give an interpretation of what the yi's are if it arises from some convergent sequences of graphs.
Again, I'd like to defer that to after the proof. This is the kind of thing I was going to discuss at the end once the proof is finished. So I'll do that if that's okay. Okay. And if the answer I give then is not good enough, then ask me afterwards. Okay. So 2 will follow if we show instead the following. We show that the probability that one of these guys, so the last one, equals 1, conditional on the yi's and all the others, is actually the same if we only condition on yim and yjm. So I have this event that this particular edge gets the value 1, and I'm conditioning on two different things. Here I'm only conditioning on yim and yjm. Here I'm conditioning on a lot more. I'm conditioning on all the yi's and the values at these edges. And all I want to prove to you is that these conditional probabilities are equal. Well, okay, this is a 0, 1 random variable, so actually it's the same if I talk about conditional expectations, which will make my life easier. And now once you know this, you get that claim number 2 by a simple induction. You use iterated conditional expectation and you find it just factorizes. So let me sketch that out for you. So let me call this 3. So 3 implies 2. You can't see this, can you? Rubbish. Okay. Let me just move this up and then bring it back. So 3 implies 2 because, and if I look at the left side of 2, again, this is the event that all these things are 1, and they're all 0, 1 valued, so it's the same as the expectation of their product. That's 0, 1 if and only if they're all equal. That's 1 if and only if they're all equal to 1. So the expectation of the product well, by the law of iterated conditional expectation, this thing is the same if I first pick 1 and condition on everything else, and then I evaluate this. So this is equal to the following. On everything else, conditioned on the yi's. This is by iterated conditional expectation. But I'm assuming I have a formula for that. This guy is just this thing. And if that's true, then this actually only depends on these two. Well, I'm conditioning on more than that, so now this comes outside. Times what's left, which is the same product I started with, but with n minus 1 random variables. So let me just say same with n minus 1. So if you know this property 3, that lets you simply take the last of these, x, I, m, j, m, outside, and then you have the same claim that you wanted with n minus 1. So you get an induction on m. So yeah, I'm just doing trivial things, pushing sigma algebras around and then seeing which one is bigger than which other one, and reduce the claims of this 3. So now I just want to prove 3. Right. Let me move 3 to the top. Actually, let me bring it down and introduce some notation. So I want to show that conditioning x, I, m, j, m on all of those things is the same as just conditioning on these two. Let me omit the m's now, since they're making my life harder. So as long as ij is not one of these other edges, this is still fine. And let me now refer to the sigma algebra generated by all of these as F1. And the sigma algebra generated by just these two as F2. So what I want to show is that the conditional expectation onto F1 of xij equals the conditional expectation onto F2 of xij. So this is just a very compact way of writing that. That's all. So this is what I want to show. Now let me put it up. And now finally we're actually going to do a little bit of analysis. Let me keep this and remove this. So observe that F1 is generated by a list of random variables that includes yi and yj. So F1 is bigger than F2, or at least as big as F2. So clearly F1 is bigger than F2. So again, by iterated conditional expectation, the expectation onto F2 is the same as if you first take the expectation onto F1 and then onto F2. Iterated conditional expectation. This is an orthogonal projection in L2 of functions. So this implies the L2 norm of this guy is no larger than the L2 norm of this guy. Is that much clear? It's orthogonal projection in Hilbert space. But moreover, they're equal, the random variables are equal only if their norms are equal. because that means I took a vector in L2, I projected it onto a subspace, and it didn't get any shorter. It must have actually not changed. So this is where a piece of analysis came from. I actually don't need to prove very carefully that these are the exact same random variables. I just need to show they have the same norm. Okay? So I've boiled it down to proving that these are equal. And I just argued that I have an inequality going one way, so actually it's enough if I prove that. So the goal now is just to prove this. So it sounds like we've boiled this down to something that looks very hard to reach, but actually we're very close to the summit now. Okay. What shall I say? Let me stay here for a while. So this is the second point and last point at which I'm actually going to use exchangeability in the following slightly magical way. Let's go over here and draw a picture of which random variables we use to generate F1 and F2. Okay? So why don't I put that up and bring this down. So F1, so each yi remembers all the zeros and ones in the region I shaded in, that bottom triangle and that line. So in particular F2, well, that's generated by yi and yj. So F2 is the sigma algebra generated by, let me just draw it like this. All the random variables down here, and the I line and the j line. That's F2. Sigma of that. And if I make it a bit smaller, I can draw F1 here as well. F1, that's generated by all the yi's, so they together remember everything in this lower region, and a few of the xij's as well. So we draw it like this. And then there's a few points up here, which are I1j1, sorry, up to I m minus 1, j m minus 1. A few points up there. Okay? So now you can see in this picture, this one I have shaded more than this one, that's why F1 was bigger than F2. Okay. So now, let me go over there. This is too far back. Now I'm going to use exchangeability again in the following rather subtle way. Let gamma, well no, first let n complement be broken into two more pieces, both infinite. So that's an infinite set. I can break it into two infinite subsets, disjoint, that's legal. And now let gamma be the following, or an injection from Z to Z with the following properties. First, it fixes IM and, well, I and J, the I and J that appear there. Doesn't move those. Second, all the other positive integers go to T, and all the negative integers go to S. There we go. So you should be thinking of Hilbert's hotel at this point. I have an infinite set, and I'm putting it inside an infinite co-infinite subset of itself. And I can do that. I haven't shown you yet why I'm doing it, but I can do it. So in terms of our picture, if you think that here we have these two distinguished points, I and j, those lines are staying fixed, but everything else up here is being moved to this side, to this set S, and everything down here is being moved further to this side. Yeah? Now, by exchangeability, the joint law of everything in sight is invariant under this guy. I proved that to you before. So let me draw a line. By exchangeability, the joint distribution of, well, let me say xkl. This is the same as if I move everybody by gamma. Okay? By exchangeability, in law, sorry. And now gamma didn't move I and j, so this implies that if I condition xij onto F1, that agrees in law with what happens if I condition it not onto F1, but under whatever I get if I use these random variables in the definition of F1 instead. We call it F3.
F3 is gamma of F1?
Yeah, so if you think of abstractly as S infinity acting on Z2, then this is the image of F1 under gamma. Yes. So abstractly, F3 is gamma of F1. But let me actually draw a picture of what it is. So F3 now, remember F1 is generated by everything down here and a few points upstairs. And F3 is going to be generated by the random variables indexed by the images of all the same points under gamma. Okay? So we draw the picture. And now down here I have also, so this is N, and this is S, and this is T. I moved a load of stuff towards the left. So the lines under I and under J, they don't move, because gamma fixes I and J. Everything else upstairs is moved to S. So this whole region and all these other points are moved down here. And everything that was in here gets moved further over. That's the same as F2. Actually, it's not, because you don't hit quite everything down here. So this is actually smaller than F2. So this image F3 is a subalgebra, sigma subalgebra of F2. So I started with F1 being bigger than F2, and now I moved it a bit, and now it's inside F2. Well, these are the same in law, so they have the same L2 norm. And now, by just the same reasoning as before, F3 is the smaller one now, so this is less than or equal to the conditional expectation onto F2. And that's what I wanted. So we're home. It's clever, it's cute. It's not totally obvious, but that's actually the end of the proof. Okay, so that's the original probabilist proof of Aldous Hoover. Yeah? Sorry? I mean, this is just an injection from one countable set to another. And then I had this argument before that if you know for bijections that you get the same law, you get it for injections as well. I mean, this is not really acting on measure spaces. I can lift it so that it's moving coordinates in measure spaces, but then it's easily seen to be measurable because each coordinate depends on just one coordinate. Okay, so that's it. That's the end of the Aldous Hoover proof. Let me try and say a few rather vague words, and there's more on this in the notes if what I say doesn't make any sense, about how this corresponds to regularity lemmas. So you stare at this proof for a long time, and it takes a while before you see where anything non-trivial was said, but actually it's worth focusing here. The heart of the proof is to show that conditioning on two different sigma algebras, one quite big and one quite small, actually does the same thing. So this xij is independent of a lot of the information that you have floating around. And you do that by showing that two L2 norms are the same. If we go back to the proof of the Semeredi regularity lemma, what does it do? It starts with the graph. Well, I just draw silly pictures. Okay, you start with the graph. You have, this is the vertex set, and this is the vertex set, and there's the adjacency matrix. And you say, if it's not regular, then I can cut V into pieces so that the energy of the partition goes up, this energy functional that Jacob wrote down in his talk. So I cut it into two pieces, and the energy goes up. And if the pieces are still not regular, I do it again. And I keep doing this, and the energy keeps increasing, and it can't go on forever, so eventually I must hit a point at which it can't increase by too much, and that implies regularity. So think of these partitions as an increasing sequence of sigma algebras. And what I'm doing is I'm watching the L2 norms of the conditional expectation of the adjacency matrix, the indicator function, on those sigma algebras as they go up, and I'm waiting till they stabilize, and they have to eventually. Here, I'm saying that, and then the point here is that once it stabilizes, once you can't push that L2 norm up further, there's an argument that says you have regularity. Here, the same thing has happened. I know once these L2 norms are actually equal, this random variable, the presence of an edge at ij, has to be independent of a load of other information. And the other information all involves how I talks to somebody else. It doesn't involve the edge ij. So what you should think of is that these yi's that we've produced by this magic trick correspond to the cells of the Semerady partition. And they capture together all the information that xij could have some correlation with that depends on how I talks to somebody else. And you can tell that you've captured all of it because of this proof that the L2 norms are equal. And over here, well, you can't just make an infinite list of yi's to begin with, so you have to construct them step by step. So you produce this sequence of refinements of finite sigma algebras, and then once that L2 norm stabilizes, for very much the same reason, for very much the same estimates, you find that what happens inside the squares is basically independent of any product set, which is a set that depends only on what this coordinate is doing times something that this coordinate is doing. And so now I was going to leave it as an exercise for enthusiasts. If you write out this proof knowing that the law you started with is sampled from some finite graph, but possibly a very big finite graph, but then you weaken the requirement to only needing approximate equality here, you'll find that in order to do that, you need to take a list of yi's that's just big enough to generate the full Semerady partition, and no more. So having a Semerady partition is the same as taking enough of a finite list of these yi's to get approximate equality here. That's a little bit vague, but I don't want to write out the full details of this exercise because it is kind of messy.
This is too soft to give you any good bounds on
Yeah, there's no bounds.
how many.
No, there's no bounds.
This just avoids that.
Yeah, we just, I mean, bounds are terrible anyway, so why not just ignore them? No, I don't mean that. I don't mean that at all. But yeah, this doesn't give you any bounds.
Okay, it doesn't give you any bounds. So you're kind of skirting all of that, whereas going through that, you are getting bounds, just making the proof more difficult.
That's right, that's right. And the heart of the difference is, this thing that you hear talked about quite a lot. If you go through the proof of the regularity lemma, you're not looking for a norm to reach its final value. You're looking for it to stabilize for a long time. Whereas here, the essential facts that make this work are the orthogonal projection properties of conditional expectation. And if you go through the proof that there is something called conditional expectation, what you're doing is taking a sequence Hilbert space and waiting till it reaches its limit. So that's where you get the difference between the finite and the infinite. Here I can wait till the sequence is actually done, whatever it's going to do, forever. In the finite world, I have to just look for a plateau and not worry about what happens afterwards, as long as the plateau is long enough. But the real point of contact between these proofs is between the regularity lemma and the proof that there is something called conditional expectation, and it's an orthogonal projection.